Hello everyone, my name is Ritik Manghani and this is my video demonstration for Milestone 3 of the AetherMart database project. In this milestone, we'll address the critical business need for 24/7 database availability by implementing and comparing industry standard high availability solutions. Here's our agenda. We'll start with a quick recap of the scalable foundation we built in Milestone 2. Then we'll dive into the core business problem of eliminating downtime. I'll walk you through our first solution, standard MariaDB replication, and then our second, more robust solution, the MariaDB Galera cluster. We'll compare them directly, discuss the key lessons learned from the implementation, and conclude with our final recommendation for AetherMart. In Milestone 2, we made our database intelligent and scalable. We implemented automated triggers for auditing, and we partitioned our large customers table to ensure high performance as the business grows. With this solid foundation in place, our next and most critical task is to ensure this database is always online. The driving force behind this milestone was a clear mandate from AetherMart's leadership. After a costly database outage, the core problem is that our current architecture, while scalable, represents a single point of failure. For a 24/7 e-commerce business like EtherMart, any downtime directly translates to lost sales and damaged customer trust. Our objective is to build a fault-tolerant architecture that can withstand server failures without any interruption to the business. Our first approach was to implement a standard primary-secondary replication setup. In this model, our uh, all write operations go to a single primary server, which then asynchronously copies those changes to one or more replica servers. This provides a basic level of redundancy and a way to offload read queries. We successfully deployed this architecture using two AWS EC2 instances. The process involved configuring a secure network, editing the MariaDB configuration files on both the primary and the secondary to establish their roles, creating a dedicated replication user for security, and finally linking the two servers. The verification was successful, which I will now demonstrate using the README document that I have prepared. So we will be following the steps mentioned in the official documentation provided by MariaDB. As you can see, we began by setting up a dedicated AWS security group to allow secure communication between the nodes on port 3306 and that's scrolling down, we can see that the exact modifications we made to the primary's config file were set where we set the unique server ID and enable the binary log. The security groups had a firewall aspect to it, which helps to protect it from any external attacks, cyber attacks. So this is the modification of the config file that I was just talking about. Here we set the server ID to 1 and we enable the bin log file. We then created the replication Ritik user with the necessary privileges. When we check the master status, it gives the position and the file where the uh, bin log will be stored. After this, we switched to the replica and updated the config file there as well. We updated the server ID there, which should not be similar to master's server ID, which is 1. So anything apart from 1 will work. For our case, we've used 2. After this, we update the master from the replica. Once this was done, and this is the code that we'll be using to do that. Once this is done, we started the start replica command. We check the status of the replica by show replica status \g. If replication is working correctly, both the values of slave IO running and slave SQL running should be yes, which in our case matches. This is the most critical verification step. The fact that both slave IO running and slave SQL running are yes gives us a definitive proof that the replication link is healthy and active. Once that is done, we started with the data ingestion part, similar to what we had done for milestone 1. So I first created a virtual environment on Python to install the CSVs using the generator py script, and then I loaded and transformed the data in all the CSVs, and yeah. So now we can see that both the data both the instances have data in them, and now our task is to match whether the records are same. We need to validate the data. So the first test that we'll be doing is to verify record counts. Here you can see that the primary and the secondary record count matches. So our test was successful. The second was for data content integrity, where we needed to check the checksum for all the core tables, all the CSV files that we had, the products, customers, orders, order times, order items, reviews, categories, suppliers. So even here the data is matching, so our test was successful. If the checksums don't match, there is data inconsistency, which for our case fortunately was not the case. Then we started with we conducted the insert, delete, and update test cases, and successfully we even verified that all of them were working perfectly fine for both the the secondary and the primary. We just wanted to make sure that all the corner test cases were fine, working fine. We even did the conceptual failover testing. So first, we set the global read only to on. So this was in case the master fails, and we need to shift it from master to the secondary. So we wait for full synchronization, show replica status, master. Seconds behind the master is equal to 0. This gives us confirmation that we can proceed, and now we can stop replication and promote the secondary to be the new primary. We then test it by writing on the new primary, which was earlier the secondary, because earlier it just had the read only capabilities. The And now we have given it the access to become the new primary. So this is the query that I ran, and the insert was successful. Hmm. And then I performed additional steps to check for the data validation. So the record counts match. We needed to do this in order to verify if the records are working, are still matching. So after the verification was completed, we know that the replication status shows both IO and SQL threads running. Record counts match across all the tables on both the servers. Checksum values match for all the core tables. Insert, update, and delete operations were successful. Complex transactions replicate automatically. Conceptual failover procedures documented. Data consistency validated after failover simulation. Now, moving back to the PPT. After testing, we evaluated the solution. While it's great for read scaling and backups, it fails to solve AetherMart's core problem. It still has a single point of failure for writes. Failover is a manual process that causes downtime, and the asynchronous nature means data could be lost in a crash. For these reasons, it's unsuitable for our critical needs. This brings us to our second, much more robust solution, a 3-node MariaDB Galera cluster. This is a synchronous multi-primary system. Any write to any node is only confirmed once. It's successfully committed on all nodes. If a node fails, the cluster automatically continues operating without any interruption. We deployed a 3-node cluster on AWS. The setup involves creating a more specific security group to handle Galera's communication ports, creating a detailed Galera configuration file on each node to define the cluster members, and then bootstrapping the first node to initialize the cluster. Our verification was successful, showing a healthy 3-node cluster. Let's look at the documentation for the Galera setup. Here is the new, more specific security group we created, opening the required ports for cluster communication, and this section shows the 60-galera.config file. So before that, we'll be using the following ports: the 4567, the 4568. These are the UDP and TCP um, protocols for unicasting and multicasting. Um, Yeah, and then we'll be using 4567 and 22 and 4444. We'll be using Ubuntu OS, and here we'll be creating three instances, and all of them should be within the same security group in order to protect our data from any cyber attacks or any other risks. So the 4567 Galera replication help is for multicasting, and this is for the UDP, and the 4567 for the TCP is for Galera replication, multicast and unicast. We launch three instances after renaming, so it's Galera A, Galera B, Galera C. For each of the instances, we'll be changing the Galera config file, and this is the 60-galera.config file that I was talking about, which is the heart of the cluster, telling each node how to find the others. We'll be bootstrapping the first node using the Galera underscore new underscore cluster command. After bootstrapping the first node and starting the others, we ran our key verification check, which you can see in this screenshot. The ws rep underscore cluster size is 3, confirming all nodes are connected and healthy. The true test of a high availability solution is how it handles failure. We conducted a series of rigorous tests to validate the cluster's resilience. Let me walk you through our most important test, a simulated node crash. As you can see uh, in the screenshot, we start with a healthy cluster of size 3. Uh, First, we'll verify if all the records are matching. We even conducted similar tests like the standard replication of inserting in one node and verifying if it reflects on node 2 and 3. So here what we did was we inserted a test product on node 1, and we verified it on node 2 and 3, that is B and C in our case. Similarly, we did an update and a delete. We were successful in verifying and validating the data after these uh, instructions operations. Similarly, we did a multi-node concurrent write where we inserted uh, a customer from all three nodes and then verified on all nodes. You should see all three customers, 1, 2, and 3, and we did that in an order to make it chronological, A, B, and C. That's when we did the we performed the disable MariaDB and stop MariaDB to make it in line with our operations like A, B, and C. And so while starting, we'll perform A, B, and C in that order. And while stopping the databases, the cluster, we'll be stopping C first, then B, and then A. We even added a new node to the cluster to verify and then remove the cluster as well. We added a new instance to the cluster and removed that new instance that we added to check for the values. So when we added it, the cluster size increased to 4 than the earlier 3, and later on when we removed it, it again turned back to 3. Let me walk you through our most important test, a simulated node crash. As you can see in this first screenshot, we start with a healthy cluster of uh, size 3. Next, we simulate the failure by stopping uh, the MariaDB server on one of the nodes. That is, we are doing it for node 3. So when we do that, the cluster size on the remaining nodes immediately and automatically drops to 2. The cluster is still online and fully functional. During this outage, we performed a write operation on one of the active nodes. Then we brought the failed node back online, as this screenshot shows. The node automatically resynced with the cluster, and the data that was written during the outage now is present on the recovered node. This test proves it has zero downtime and zero data loss. So milestone, the Galera A and Galera B were showing like 2. The cluster size on them was 2, and then we had 2 insert operations on them. This was the operation, and then we bring back the uh, node 3, MariaDB on node 3, and then we verified it on node 3, which is C in our case, and we can see that it successfully ran without any data loss. This direct comparison reveals critical trade-offs for AetherMart's architecture. While Galera has higher performance, overhead, and complexity, its multi-primary availability, automatic failover, and strong data consistency are non-negotiable for our business. For AetherMart, critically transactional data, Galera cluster is the superior choice, though we acknowledge that semi-synchronous approach could be a viable compromise in some scenarios. So my recommendation for AetherMart is to use Galera cluster. Like, however, that there are trade-offs. That is, has, including the latency and the complexity. But uh, we can even go with semi-synchronous. Uh, Moving on, the AI usage and the lessons learned. I used AI as a collaborative partner for this milestone. It provided the initial guides and testing scripts, which I then executed and validated. The most critical lesson I learned was the importance of networking. A small mistake in the security group rules can prevent a cluster from forming. The hands-on failover testing was also invaluable, as witnessing the cluster heal itself provides a level of understanding that documentation alone cannot. In conclusion, we have successfully transformed AetherMart's database from a single point of failure into a highly available, resilient platform. We have proven through rigorous testing that a Galera cluster can withstand node failure with zero downtime and zero data loss. AetherMart's infrastructure is now ready to guarantee the 24/7 availability that our global e-commerce business needs. Thank you so much for staying through the presentation. For any questions, please uh, don't hesitate to reach out. Thank you so much. Have a great day ahead.